everyone, welcome back. In this video I'm going to use rotational kinematics to solve some of these problems. So I'm going to give you and show you some examples on how to apply the concepts that we've just learned about to kinematic problems. The good news is they're kinematic problems. So the best way to kind of solve these is treat it like kinematics and recognizing what information you have and then matching it with the correct equation, with the most efficient equation I should say, and then solving accordingly. So here's a typical problem. So this is a fan. A cooling fan is turned off when it's running at 850 revolutions per minute. It's asking for, here let me do this really quick. There we go. It's asking for what's the fan's angular acceleration assuming constant and how long did it take to come to rest. So first let's organize our information before we even think about what to solve for, because you should recognize what these mean. So first of all, this 1850 revolutions per minute is an angular velocity. Now the reason why I know that's an angular velocity is because we have a distance and a time. And it's not squared, so it's not acceleration. And it has a distance and a time. If it didn't have a time, it would just be an angular distance. So, in fact, let's take a look. A cooling fan is turned off when it is running at that speed. It has this many revolutions before it comes to a stop. So that's information too. So this is the initial because it started there, and this is the final because this is it says it comes to rest. So information I have right now is 850 revolutions per minute, and they have omega final as 0. Now we always want our units in radians per second, so we will have to convert this. I'm going to wait to do that, but that's what we'll do here. Let's see what other information. 1500 revolutions. That is an angular displacement because we just have a unit of angular distance right here. So that's going to be theta. So it's like our distance. Once again, it's in revolutions. We need to be in radians, so we have to convert. So we're looking for, part A is looking for angular acceleration, part A, and part B is looking for how long time. Oops. I don't know why I wrote it like that, but that's the way I did it, right? Okay, so first step, extract your information. It's very important that you do this because I think having this visual is so helpful in understanding what you have and what you know. Extract information and then, of course, assign variables. So what is an angular velocity? What is that? Etc. 2. Convert values if needed. You must have it always in radians, so we must do that. And then after we do that, we can select our equation from our kinematics. And then, of course, solve. And then 5 checks. Check your answer. That's my problem-solving technique. Problem solving. So I did part 1 already. So now I'm going to convert all those values, okay? There we go, a little snapshot of myself. It's so silly. Okay. I'm just going to rewrite this number. So here's the conversion. I know in 1 revolution, there are 2 pi radians. Oh, I'm sorry. Let's fix this. Let's start over. There we go. I missed revolutions per minute. There we go. That's better? And I'd like to write it like this because I think it's easier for me to convert. So I know in 1 revolution, pen is stuck. I don't know why. Sorry folks, I don't know why my pen is stuck here. Give it a second, let me see if I can fix it. Okay, I don't know what happened there, sorry. So 1 revolution, there's 2 pi radians. And then I had to take these minutes into seconds. So 850 times pi times 2 divided by 60 gives me 88.97. This is in radians per second. So we're now in the right units. This 1500 revolutions needs to be in radians. So times in 1 revolution, there's 2 pi radians. Oh boy. Pen is not agreeing with me. I think it's dying. Yeah. Bummer. So 1500 times 2 times pi. The revolutions cancel, we're left with radians. Okay, now that I have these and some, values that we can use, we can go ahead and solve our problem. So I'm just going to rewrite what we have. Let me see. My pen keeps dying, which is frustrating. Right on my screen, which is not helpful. 9.7. It's not as neat either. Omega final is 0. This is 9420 radians. And then I need alpha. So I need to find a kinematic equation that has omega I, omega f, alpha, and theta right here. So if you look through the kinematic equations, should be alpha, theta. That's the one. Because if you look here, 0 radians per second squared, squared, is equal to 88.97 radians per second squared plus 2. Alpha is what we're solving for, and this is 9420 radians, like that. And that's our setup. So I'm just going to go ahead and skip the algebra and go right to solving this out. 88.97 squared. I'm going to subtract that over to the other side. Divided by 2, divided by 9420. So I get negative 0.42 radians per second squared from this. So it means that we are essentially slowing down, because that's what the negative side represents. We started moving fast and then we're going to rest, so we're slowing down at 0.42 radians per second squared. So that's our answer. So now the next question is, what is time? How long did it take to do this? And we can, since we have acceleration now, we can use pretty much any kinematic equation. The one I like is this one because it's the easiest. And then I'll plug in my numbers. 0 radians per second equals the initial, which was 88.97 radians per second, plus negative, sorry, I'll get that in a second, times t, sorry about the pen here. Alright, if I solve for t, 88.97, move that over, becomes negative, divided by 4.42, takes 211.83 seconds. So, just because I'm curious, this is about 3.5 minutes. Interesting. But this is the official answer, like that. So if you notice here, essentially all I'm doing is using kinematics. The extra step comes from the following. Being able to understand what these values mean and being able to assign them to their correct variable, and then taking these and converting them to radians. I mean, those are the biggest two challenges you're going to have with this section, because essentially it's all kind of the same in terms of kinematics. So let me get out of here for a second. And then these are more of the same. In fact, I'm going to just let you try these on your own so you can see how you could figure out. The solutions are in the notes in the bottom of this PowerPoint. But it's the same kind of concepts. But notice, again, you have revolutions per minute. You've got to calculate and convert that into radians per second. You know, if you have the rotational velocity, you can get the linear velocity if you have the radius, which you do. So it's not too bad here. So that's it. You're just basically thinking in terms of circles instead of in terms of lines, and that's the biggest difference with rotational kinematics. So, some big things here I also want to point out are these equations, right? So I introduced these right now, but we're going to see this common factor of r going from one unit to the other. Now, our next lesson is going to be rotational torque, but notice that torque is basically the radius of your level arm times the force. Of course, this will make a little more sense, but the point I'm making is notice that we can go from a linear force to a rotational force by a factor of r. And same thing, we're not there yet, but we can go from a linear momentum, mv, to an angular momentum by a factor of r. So this is how we're going to go from one mode to another, from linear to rotational. And of course, we'll see these trends as we move forward. Lots of extra problems, because why not? It's really helpful. It's kind of hard for most students to get their minds in terms of spinning, because it's not something we really think about. So the more problems you do, the more comfortable you get. I find that once I did a few problems, I was fine, but the first couple I was like, whoa, what's going on? Because it's a totally new way of thinking about spinning. So these are just extra problems with the solutions right here, so you can try out your understanding with that. Okay, if you're in my AP class, we'll be doing a rotational lab where we're going to take this, this is called a rotational demonstrator, and you're going to find the angular acceleration. So we're going to put a mass on that. We're going to allow that to spin and get faster because that's going to pull it, which is going to cause it to spin faster. And we're basically going to measure the change of spin. We're going to measure two ways. We're going to use rotational kinematics the way that we learned before. So essentially we can use something like theta is equal to omega I t plus 1/2 alpha t squared. And then this one we're just going to find the linear acceleration. And then we'll find the linear acceleration and we'll find r and just basically calculate it. Since we're measuring the same feature of this, acceleration should be the same value whether we measure kinematics or through the conversion. But as always, we'll see which one's more accurate in doing that. So we're going to look at that. Okay, this concludes angular kinematics.